So first of all, I would like to say konnichiwa and thank you for giving me the opportunity to have this lecture, not only for the master students, but also for the bachelor students. I'm very happy to see you. And I would like to add something about me and the place where I'm working and living. As you already know, my name is Dietrich Albert. And to be honest, my given name is Dietrich and my family name is Albert. In Europe, this quite often is mixed, changed, because Albert is also a very common given name. And I'm a professor emeritus of Graz University, or University of Graz, and for more than 17 years. And I'm also a senior scientist at Graz University of Technology, and I'm still working there. That's the reason you find two of these icons, Uni Graz and TUG, which is Graz University of Technology. My scientific background is psychology. However, I lead an interdisciplinary team with psychologists, mathematicians, and computer scientists. And the two universities are located in a city southeast of Austria, which is a country, as you know, in Europe. And this city is really worth to visit, not only because of me and the two universities, but there's also something to see. For instance, this city has two cultural heritages. One is the city center, the old part of the city. The other one is a castle called Eggenberg. In Eggenberg, for instance, you can find an old Japanese paravent with a very nice old picture of Osaka. So it's worth to go also to Eggenberg. Furthermore, I want to argue that Graz is very famous because it's the largest armory in the world located in the city of Graz. So very many old weapons. You would say weapons of samurai, however, in this case, they are knights from ancient times, and the people of Graz who wanted to fight, or let me say, to protect the city against foreign troops. And it's really worth to visit also this place. And in more recent time, Graz is also famous because it's the home of an American governor of California. Maybe you know him from his movies, and because he also was a bodybuilder. His name is Arnold Schwarzenegger. He is coming from Graz. So please visit this place, the universities, the city, and the Schloss Eggenberg. Now we want to start with our lecture, which is on how to generate knowledge and competence spaces and how to validate them. You probably already noticed that my mother tongue is not English. My mother tongue is German, so I'm not a native speaker of English, so please do not take me as a model to learn English. We want to learn about knowledge spaces and how to create them. So let's continue, and this is the overview. We'll have an introduction. We have the basics of knowledge space theory. We have the demand component approach, the competence performance approach, the ontology-based skill approach, and we will also briefly go through the topic of validation and, of course, final remark. So let's start with the introduction. The question is how to create knowledge structures and how to validate them as the basis for adaptive, individualized e-learning systems, allowing for adaptive testing and personalized learning and teaching. This is our question. And our basis is knowledge space theory and the competence-based knowledge space theory, which is an extension of knowledge space theory. And the question is how to build the knowledge structure. And there is one approach which is querying experts. This is the approach which has been used and is used to create the structure which is used in the commercial system ALEX, which I really recommend to visit, because you can test your knowledge, for instance, in statistics and mathematics and in other contents. And another possibility is to analyze large samples of responses of students, which is also done by this system ALEX. A third approach is identifying relevant problem components, attributes, and their respective difficulty and demands by cognitive demand analysis. So this is the demand approach, which is used in the tiny demonstrating system RAD. Another approach is psychological analysis of the competencies required to solve the problems. This is the competence performance approach, which is used in the system APPLES. And finally, we want to show to derive skill structures from competencies and action structures based on ontologies. That's the skill approach, which is used in the I-class project. So let's start with the knowledge space theory. We only will have some very basic information about this and cannot go into the upper level. On the other side, those of you who are interested in this can try to find themselves by studying the literature. So the basic concepts of knowledge space theory are the knowledge domain, the prerequisite or precedence relation, also called surmise relation, the knowledge state, the knowledge structure, and the knowledge space, which is a special knowledge structure, the learning path, and the learning goal. So I will try to explain very briefly these basic concepts. Let's start with a simple example. Here we have 5 problems from mathematics or arithmetics, and as you easily can see, these problems are not of equal difficulty, and there might be some structure on it, some prerequisite structure. That means that if a person is not able to solve one, let me say, simple problem, that this person also will not solve a more harder problem. So the question is, what's the structure? If you go into details and analyze these problems or ask the experts, you probably might find this kind of structure. That means that, for instance, if a person is not able to solve this problem A, then this person should also not be able to solve the problem B, D, and E. Nothing can be said about solving C, because A and C are not connected. So this is a so-called Hasse diagram, which is the illustration of a partial order. Partial order has special properties, especially transitivity is mentioned, also reflexivity and anti-symmetry. And so please take this as an illustration, as a visualization of this special structure. And in this talk, because we have a lot of bachelor students also among us, I will try to avoid to use the mathematics behind these things. This is very important to understand. Do you have a question to interpret this structure? Okay, so here we have the prerequisite, surmise, or precedence relation for these 5 problems, and they define not only the knowledge domain, which is called Q in this case because of the term questions for this example. And what is very important is that this prerequisite relation induces a knowledge structure with a knowledge states. Mathematically spoken, this knowledge structure is a lattice which has some nice properties. In this very simple case, it's closed for union and closed for intersection, and also the empty set and the full set Q are elements in this set of, in this case, knowledge states. And as you easily can see, this collection, this set of knowledge states is a subset of the power set of all the 5 problems. And the reason for that is that some of the, in principle, possible combinations of solving the problems are not in accordance with this prerequisite relation. For instance, that it's impossible that a person solves D and B. This combination cannot be a knowledge state, because if this person is able to solve these 2 problems, this person also should solve A. So D, the state dB, is not possible according to this prerequisite relation. That's the main reason that we have a subset of the power set as the collection of knowledge states. Furthermore, we have this symbol. That means there is a one-to-one correspondence between the prerequisite relations and the knowledge structure, which is a knowledge space on the right side. The reason for this is that there is a famous theorem by Birkhoff from 1937 that there is a one-to-one correspondence between the partial orders and the lattices. This theorem later, in 1985, was generalized by Dorian and Falmanier. And this generalization and the interpretation in terms of knowledge was the starting point of the knowledge space theory. So very important that we have this one-to-one correspondence. So if you work with this structure, you easily can generate this structure, or if you work with this structure, you easily can generate this one. The question is, because this is also a Hasse diagram, how to interpret. In this case, these lines connect those knowledge states which are subsets of each other. So the state AB is a subset of all these other 5 states above. And the states below, in this case A and the empty set, is also a subset of AB. Of course not AC, because they are not connected. So that means you can easily compare the persons which represent these knowledge states by subset relation. Do you have a question regarding this? Okay. So we argued there are some basic concepts which can be easily defined. In this case, it's the learning path and the learning goal. The learning path in this case is illustrated by one of the possible learning paths, going from knowing nothing, empty set, to the goal state in this case, which is the state Q. Of course, here are other possible paths. For instance, this one, or this one. So you easily can imagine how many paths in this simple example are possible. In any case, there is not a very strict sequence of learning in our case, because you have options. However, the number of options is restricted by the knowledge space.